be able to respond whether you can hear me or not. Who is volunteering?
I'm volunteer.
Who is that?
Abigail.
Abigail. Okay. So just as a recap, last week we did probabilities. You'll see where they'll come in today. So we can use probabilities to model events, as in the chances of some events occurring. But all statistical models are also pegged on some probability distributions. So as you'll see, we'll be discussing different statistical models, and this will be tied to the different probability distributions that we discussed last week. Also recall that we had discussed that the simplest model that you'll always be interacting with is the simple linear regression model, where you have one dependent variable which is continuous and you have one independent variable. Then in that case, you can model it using simple linear regression model. Then we also saw last week but one that if you have more than one independent variables that are influencing the dependent variable, then you'll be dealing with multiple linear regression model, where still the condition of y being continuous is still there. And we also learned that another name for multiple linear regression model is the general linear model, And still the condition is there that for general linear model, the y must be continuous. Y continuous, what does this mean? It means that that dependent variable y can assume decimal values, that you can have something when you record it, you can have decimal points. That's what we mean by continuous. What does it mean if it's not continuous? If it's not continuous, there are several options. Regularly encountered options is when it's categorical. For example, it has two categories. Malaria status positive or negative. A household is food secure or food insecure. You spray some insects with some insecticide, some die, some don't die. Then you have two categories. In that case, then it's not continuous, it's categorical. So you cannot have 1.5 there. Then another scenario is when your response variable is a count. For example, how many siblings you have. Then in that case, you cannot have 2.5 siblings, so it cannot be continuous. Then in those cases, the general linear model does not hold. So when the general linear model does not hold because of violation of some assumptions, for example, the first key assumption that we are going to relax is the issue of the y variable being continuous. So if the y variable is not continuous, then we look at other models. And a general name for the models that we'll be looking at for y not continuous is what we call the generalized linear models, into bracket GLM. So there are two terms there that, two phrases there that can be confusing. There is general linear model, which doesn't have an acronym. And the other one is the generalized linear models, which has an acronym of GLM. Is that okay?
Yes.
Okay, so I expect you to respond a little bit faster than that so that we don't waste any seconds. So we are shifting from general linear models to generalized linear models. I had introduced specific ones, and I said that we were jumping the gun to go and look at those models so that we appreciate them. Then we come now and understand the nitty-gritties within those models. Why do they look the way they look like? Is that okay?
Yes.
So the generalized linear model, if you can see my screen, this was introduced by Nita and Wedenberg in 1972. The generalized linear model. So basically, they were introduced to be able to cater for cases where the dependent variable is not continuous. And the generalized linear models, they have three components. Any GLM model has three components. The first one is the random component. Abigail, can you read for us?
It's not very visible. The writings are really tiny, but I can use my copy. Okay.
Okay, you can also use
The structure of generalized linear models. A generalized linear model consists of 3 components. Number 1 is the random component, which specifies the conditional distribution of the response variable y, given the values.
Leave it there.
Okay.
So the first part is the random component. The random component here just specify what probability distribution the response variable or your dependent variable y follows. Does it follow normal distribution? Does it follow Poisson distribution? Does it follow Bernoulli distribution? Does it follow binomial distribution, or which distribution does it follow? So you have to specify the distribution of that random variable. Is that okay?
Yeah.
The second part?
Still under the random component, or the second component?
The second component.
The second component is the linear predictor. That is a linear function of regressors. Okay.
Remember, allow me to write on the screen. I hope I should be able to write. Let me try to. Okay, so I'll write on the screen, then I'll cancel this. So remember the multiple linear regression model, yi is equal to beta naught plus beta 1, x1 plus beta 2, x2 plus epsilon I. Is that okay?
Yes.
Now, this part, which has the explanatory variables or the independent variables, so which has the betas, the coefficients, together with the x variables. This part is what we call the linear predictor. Is that okay?
Yes.
So it does not contain the error term. So the linear predictor contains just the beta naught and the betas times the corresponding x values. That is what we call the linear predictor. Is that okay?
Yes.
Okay. Okay. Proceed to the third component.
The third component is a smooth and invertible linearizing link function, which transforms the expectation of the response variable to the linear predictor.
Guys, this is important. So let me put the screenshot again. So remember, we have your dependent variable, yi. Is that okay? Which is your response variable, whatever it is. Then we say that this response variable will be following some probability distribution. Some probability distribution. Is that okay?
Yes.
Give me an example of any probability distribution that you know. Parfait?
Yes, Bernoulli.
Bernoulli distribution. Bernoulli distribution has how many parameters?
1.
One parameter. What is the name of the parameter? It's the PI, or the probability of success. Is that okay?
Yes.
Is that okay? And another person, not Parfait, I need to call names now. Now, unfortunately, I have to discard the screenshot for me to be able to call names. So I'll ask questions to Calvin Otieno. That is number 1. I'm nicknaming you number 1. So when I say number 1, I will need your response. Then we have Consolata, take number 2. John Andrew, number 3. Patricia Ojijo, number 4. Rashid Shukran, number 5. Stephen Oganga, number 6. Peter Wabuya, number 7. Khaemba, number 8. Marindi, number 9. Amos, number 10. So let us then Jeff Kosgei, Abigail, number 11. So let us start with those ones. So when I say a number, the owner of the number needs to take that question so that I don't need to remember the names. So allow me to write again. So remember, for example, if yi follows Bernoulli, which I'm just trying to get an example, and Parfait, I said that, he remembers the Bernoulli distribution. which has pi. So number one, who was number one?
Yes.
Who is that?
This is Kevin.
Kevin. Okay. What was the mean? What was the mean expected value of y if y follows Bernoulli? You can check in your notes. No rush. What was the expected value of y if y follows Bernoulli distribution with parameter p? And also, what is the variance of y?
I think with parameter p, we just have the y follow.
Are you doing
Bernoulli
guesswork or you are looking at your notes? If you don't have the notes, let us know so that you don't do guesswork.
Yeah, the mean is p. Yeah?
The mean is p, correct? And the variance?
I think the variance was also defined as p, if I'm not wrong.
Are you looking into your notes or guessing? So it was p into bracket 1 minus p. Is that okay?
Yes.
Now, help me read before you go. What does the link function do? Number three. Just read on the screen. What does the link function do?
A smooth and invertible. That one?
Yes.
A smooth and invertible linearizing
But I need you to read it, then you respond to my. The answer is there, so I just need you to read it. Sorry, I need to ask you the question, then you respond. You can read it first, understand it, that number 3, then respond to what I'm asking. Is that okay? So
okay.
the answer is there in line 3, but understand my question, then answer. Right? Is that okay? So what does the link function do in a GLM?
I think it's used to connect the expected value of the response variable to the linear predictors.
It connects?
It connects the expected value of the response variable to the linear predictors.
Okay,
that
so it connects the expected value. So what is the expected value of the response variable in our case here, the one that we are dealing with? What is the expected value of the random variable?
Expected
value? We are dealing with the Bernoulli. Yeah.
This is the p into 1 minus p.
You saying?
The expected value is the same as the mean, eh? The variance, is it? Not.
Both. So what is the expected value of y for Bernoulli?
Can I help?
Yes, do.
It's p.
So the expected value is p. So what does the link function do? So if you read number 3, you'll get the answer from it for it. What does the link function do?
It transforms p.
It transforms p, so it works on p. Is that okay? For example, if that link function is assuming that we call it g, so the function g will work on the p. Is that okay? Where are you getting this from?
The statement.
So it's on the line which transforms the expectation, right? You are getting it from there, right?
Yeah.
So assuming that this g is what we call our link function, remember what you did in high school or primary, is it high school? Where you used to use f as your function, f of x, g of x, something like that. So this is just the name of the function, and we are just calling it the link function, the g. Is that okay?
Yes.
So the g operates or transforms the mean, and in our case here now for the Bernoulli, the mean is p, so it means it works on p, then it directly equates it to what?
The linear predictor.
It connects it to the linear predictor. And what did we say our linear predictor is? It is the beta naught plus beta 1 x1 plus beta 2 x2. Is that okay?
Yes.
So in the example that we have on the screen, this part which specifies the distribution is the first component. And what is the name of that first component?
The beta naught.
Random component.
Am I speaking Greek? Is my network okay?
The first component is the random.
Yes, it is
my
okay.
network okay? Or am I
Yes.
speaking Greek? It must be one of those two things.
Your network is okay, sir.
So it's me speaking Greek.
No.
So may I repeat my question? I'm saying now the random part of GLM, the random component, just gives the distribution of the response variable. Is that okay?
Yes.
Which is this part here. This part here. Can you see it's giving the distribution of the random variable?
Mm-hmm.
And what is the distribution?
Bernoulli.
Bernoulli distribution. Then the second part is the linear predictor, which is just the beta naught plus beta 1 plus beta 2 beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3, depending on the number of independent variables. Can you see it there?
Yes.
Then the other part is the one that is the link function, which works on the mean or the expected value of the random variable. And the expected value is p, so we have p inside the function. So it means our link function is this g. So this part is what we call the random. This part is the linear predictor. And this g is what we call the link. Is that okay?
Yes.
Just as a recap, a GLM model has how many components? We need somebody else. Ian Joroge.
3.
3 components. Which ones are these?
Random, link,
the link,
and the prediction.
Linear predictor.
Yeah.
Amos Wanyama. Amos Wanyama. Calvin Otieno.
Yes.
What the first component is random.
Mm-hmm.
What does the random part entail? What does it tell us?
I think it specifies the distribution of the response variable y.
100% correct.
Mm-hmm.
John Andrew. John Andrew.
Yeah.
What does the linear predictor entail?
Linear predictor entails beta naught up to beta 2x2 minus the error term. Error term doesn't include.
It's not included, right?
Yeah.
So the linear predictor is just the linear combination of the betas together with the independent variables x's. So it is the beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3, like that, depending on how many independent variables you have. Is that okay?
Yes.
Patricia Ojijo.
Yes.
Patricia?
Yes.
The third component is the link. What does the link function do in the GLN?
I think it transforms the variable within the
Nope.
equation. Yeah.
I need it crisp. No. You're almost there, but it's not correct. Yes, you need to start with the phrase it transforms. But what does it transform?
Okay. It transforms the expectation of that variable within the equation.
Which variable? There are
So
many
in our
variables.
case,
There is dependent variable, there is independent variables.
it's
So you cannot
the
just say that variable.
The dependent
Kindly
variable.
repeat. Kindly repeat.
So it transforms.
Mm-hmm.
It just transforms the expectation of the, let me say, y variable.
Mm-hmm.
In the linear predictor.
Into the linear predictor. Is that okay?
Thank you.
Yes.
Okay, great. So, guys, we've just been talking about the link function. Is that okay?
Yes.
You remember last week we did, last week but one, we wrote down logistic regression. You remember logistic regression?
Yeah.
Logistic regression, right? Wait. So how did we write it? It was yi. So this is logistic. It was yi follows Bernoulli with parameter p, and logit of p is equal to beta naught plus beta 1 x1 plus beta 2 x2. Is that okay?
Yes.
So this is logistic regression. Is that okay?
Yes.
Where is the random part? The names now. Which name did I see there? Nevin or Neville?
Yes, yes.
In this logistic regression that I'm showing on the screen,
Yeah.
Can you see the random part?
The random part is P.
I didn't hear anything.
It's P.
Nope. Another person? Any other person?
Can I try?
Yes.
It's yi follows Bernoulli's principle with parameter p.
Exactly. Just the distribution. Yi follows Bernoulli with parameter p. That is the random part. Is that okay?
Yes.
Another person, any volunteer. Can you see? So this is the random part. Okay. Another person, can you see the linear predictor?
Yes. I can try.
Who is that?
Consolata.
Consolata, please shoot.
It's the part from beta naught to beta 2.
Correct. It is the part from beta naught to beta 2x2, that part. This is the linear predictor. Another person, the third component is the link. Any person? What is the link?
Logit.
The link is the logit, this big blue. This is the link. And you can see it is working on the mean or the expected value of y, which is the p. Is that okay?
Yes.
Okay, we go to Poisson regression. Is that okay? For Poisson regression, it is yi follows Poisson Poisson distribution has how many parameters?
1.
And which symbol do you usually use for it?
Lambda.
Lambda, correct. And what is the mean for a random variable that follows Poisson with parameter lambda? What is the mean and what is the variance?
Lambda, both.
Both of them are lambda. So, but we need to put the linear predictor path. So beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 is equal to, then this is log of lambda. Is that okay?
Yes.
Another volunteer, can you show me in this Poisson regression, can you show me the random component of the GLM? Or can you tell us the random component? Any volunteer? Because if I leave the screenshot, if I leave the screen, then I lose what I'm writing. Any volunteer? Did we have a Rashid in class? Okay, any volunteer?
I think the random component is yi follows a Poisson distribution with parameter lambda.
100% correct. Who is that?
Stephen Oganga.
Stephen Oganga, thank you. Another person, can you show me the linear predictor in this Poisson regression?
Linear predictor is beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3.
Correct. This part is the linear predictor. Another person, the link.
The link is log.
The link is log. Is that okay?
Yes.
Guys, something a little bit confusing, but let me just try and if I can pull it through. Something we call the simple linear regression model that you have done, simple linear regression model. It is given by y is equal to beta naught plus beta 1 x1 plus epsilon I, where epsilon I is normal with mean 0 variance sigma squared. Is that okay?
Yes.
We can get the expected value of y from this model by just applying expected value of y through the model. So it will be expected value of beta naught plus beta 1 x1 plus epsilon I, which is equal to expected value of beta naught plus expected value of beta 1 x1 plus expected value of epsilon I. Is that okay?
Yes.
But beta naught, beta 1, all those are constants. Is that okay?
Yes.
What is the expected value of a constant?
That constant.
It is that constant, correct? Plus expected value of beta 1 x1, because beta is a constant, x is an independent variable that we know. We don't have a distribution for it, so it will be treated as a constant also. So beta, which is a constant, times x, which is a constant times a constant is most likely a very big constant. Is that okay?
Yes.
So what is the expected value of beta 1 x1?
Beta 1 x1.
Beta 1 x1 plus what is the expected value of epsilon I?
0.
It is 0 because from here we've been told that the mean of epsilon I is normally distributed with mean of 0. So it means that the other name for expected value is just the mean. Is that okay?
Yes.
So then it means this is 0. And what about the variance? So it means this is the mean of y. Is that okay?
Yes.
This is the expected value of y. What about variance? Do you agree with me that variance of yi is equal to sigma squared I need to write on the screen. Guys, if it's not clear, let me know. So variance, remember that yi is equal to, let me start from the top. Yi is equal to beta naught plus beta 1 x1 plus epsilon I. Epsilon I is normally distributed, means 0 variance sigma squared. Is that okay? So
Yes.
we've already seen that expected value of yi will be equal to beta naught plus beta 1 x1. Is that okay? The error term disappears because the mean is 0. Is that okay?
Yes.
So the variance of y will be equal to variance of beta naught plus variance of beta 1 x1 plus variance of epsilon I. Is that okay?
Yes.
So from this, variance of y is equal to what? What is variance of beta naught? Beta naught is a constant. Is that okay?
Yes.
If something is a constant, how much does it vary? How much does it change?
0.
Doesn't change.
It
0.
changes by 0. So it's 0. What about variance of beta 1 x1?
Also
0.
0.
Because beta 1 is a constant, x is a constant, because x we know it doesn't have a distribution. Only y has a distribution and x has a distribution. Sorry, and epsilon has a distribution. So x is a constant. So x times beta is a big constant. So the variance of a big constant is 0. Plus, what is variance of epsilon?
Sigma squared.
Sigma squared from here. Is that okay? So
Yes.
it means that the variance of y is sigma squared. Is that okay?
Yes.
So the mean of y is this, and the variance is this. But this will still follow normal distribution. It mean beta naught plus beta 1 x1 and variance sigma squared. Is this okay from the derivation? Because we've
Yes.
derived that we found the mean of y and also the variance of y. And we know that the error is following normal, then the y will also follow normal. Is that okay?
Yes. Yes.
Guys, is it okay if I give a notation of this part here, because it's the mean? Is that okay?
Mm-hmm.
Can I just call it mu so that we know it's the mean?
Yes.
So that I write this one now afresh as y follows normal with mean mu and variance sigma squared, and the mean mu is equal to beta naught plus beta 1 x1. Is that okay? Is it the same
Yes.
as what we have here? Is it the same as this one?
Yeah.
Is it the same as that? I've just given this an acronym to this part here that the one that I labeled here as beta naught plus beta 1 x. I've just denoted it as mu. Is that okay?
Yeah.
Guys, do you see anything strange here? Do you see anything strange here? What is this? Do you see anything strange there? Does it look like a GLM?
Yes.
What is the random part?
The random part is y follows normal mu, comma, sigma squared.
Correct. This is the random part.
No, alisutusumbua sana. Nilikupa na support ni kama nilikuwa nakulia kampani nyingine.
Sasa huyu, if we tell the guy to give us a cut for him shortchanging the company, he will refuse. Boss, we've had the secret that you are cutting deals. Okay, will we proceed? Still continuing.
I think you will be coached.
Unfortunately, if I leave the screen, I lose.
No,
my
I'm
writing.
saying Abigail is the co-host.
Oh, Abigail, are you the co-host?
No.
I think he has already muted himself.
Oh, okay. Okay, then you proceed. But we've already picked the secret, so he better pay us for keeping quiet. We heard that he's telling somebody else that that she's smart, so we are planning to use that information against him for our benefit, of course. Okay, so this is the random part. Is that okay? Can you see the linear predictor?
Yes. The linear predictor is beta naught plus beta 1.
Correct. This is the linear predictor. Is that okay? Can you see the link? Patricia? Patricia? Ojijo?
Yeah.
Remind us, what does the link do?
The link, it transforms the expectation of the y dependent variable.
Of the y, correct. So do you see what is the expectation of the random variable y? What is the mean of y? In our context here. Is there?
This signal simple here.
Is there?
Yeah.
Mu.
Yes.
Is a mu, is that okay?
Yes.
So what is our link function? Can you see our link function? Patricia?
Yes.
Can you see our link function?
Yes, I can.
What is our link function?
It's the mu.
What does the link function do?
It transforms the expectation of the y.
And what is the expectation of y in our context here? Huh?
Someone else can try assist.
But I've just asked you what you've answered. What is the expectation of, I just want you to answer that bit, then somebody else can assist now. What is the expectation of y?
Transforms the...
What is the expectation of y?
So it will be transforming the linear predictor.
No, I'm asking you, what is the expected value of y?
The expected value of y, it's mu.
It is the mu. Is that okay?
Yes.
It is the mu. I don't know if I've used that color already. It is this mu here. Is that okay?
Yeah.
Now, where is the link function?
Is there a link function really?
That is a good question. Is there a link function really? But we need the link function. It seems like it's not there, right?
Yeah.
But we need it. Is that okay? So it means there is a link function which is g. I'm just giving it a general name g. Is that okay?
Yeah.
That if it works on the mu, it gives you the mu again, so that this is still correct.
Okay.
So it must be a special link function, right?
Yes.
From high school, you did matrices, right?
Yes.
There were matrices that if you multiply them with any other matrix, they give you the same matrix.
Identity matrix.
Identity matrix. And that matrix was made up of main diagonal it was having the ones, then off diagonals it was having zeros. Is that okay?
Yeah.
Similarly, function, there is also an identity function. Identity function is any function that if you give it any input, it returns for you the same out input. It gives you back the same input. Is that okay?
Yeah.
For example, if you give it 10 shillings, if you give the function 10 shillings to do something with it, it returns for you the 10 shillings again back. That is called an identity function. Is that okay?
Yes.
So for us to be able to have this as a GLM, then it means there's a hidden link somewhere there. Is that okay?
Yes.
Which is an identity link, so that it operates on mu and returns the mu. Is that okay?
Yes.
So then it means that we can actually write the simple linear regression model in GLM framework, but the link function, we have to say that the link function is an identity function.
Yeah.
Is that okay?
Yes.
Let me just recap this. With my screenshot again. For logistic regression, I'm just doing it quickly. Guys, by the end of this unit, you should be just conversant with logistic regression, Poisson regression, and simple and multiple linear regression. Those ones you need to be having them on your fingertip. That's why I keep on repeating them regularly. So for the logistic regression, it is Y follows Bernoulli with parameter P, then logit of P is equal to beta naught plus beta 1 x1. Let me just use a simple linear regression. One independent variable only for simplicity. Then we have Poisson regression, which is Y follows Poisson with parameter lambda, then log of lambda is equal to beta naught plus beta 1 x1. Is that okay?
Yeah.
And we've also seen that actually we can write the simple linear regression model, the simple linear regression model, we can write it in GLM framework as follows. Y follows normal with mean mu and variance sigma squared. Then mu is equal to beta naught plus beta 1 x1. Is that okay?
Mm-hmm.
So what is the link function for logistic regression?
Logit.
Logit. What is the link function for Poisson regression?
Log.
Correct. And what is the link function for simple linear regression model?
Identity.
Identity. So that it gives us back the mu. Is that okay?
Mm.
By now, I would be expecting you guys to ask me, where do we get these link functions from?
Mm.
Where did we get this logit from? Where did we get this log from? Where did we get the identity? Let me put it here, I mu to be equal to mu. I mu to be equal to mu to represent identity so that it gives us the same thing. Where do we get them? Is that okay?
Mm-hmm.
To understand where these link functions come from, we must understand something we call exponential family distribution. Exponential family, exponential distribution family. Is that okay?
Yes.
Exponential distribution family. For us to understand this, if you look at the table that we have on the screen, it gives you all the link function for the different, some common link functions. It tells you that there's identity link, there's the log link, there's the inverse link, there's the inverse square link, there's square root link, there's logit link, there's probit link, there's log link, there's complementary log link. Is that okay?
Yeah.
But the question is, why can't Bernoulli have a log link? Why does it have a logit link? Why not have a log link on normal? Sorry, on simple linear regression. Why does a Bernoulli have logit and not any other thing? Is that okay?
Yeah.
For you to understand that one, you must understand something we call the exponential distribution family. Is that okay?
Yes.
In the probability distributions that we discussed last week, some of them belong to the exponential family, some of them do not belong. Is that okay?
Mm-hmm.
And I'm stopping, I'll stop sharing this. I'll share the screenshot. Let me stop sharing this first. Stop sharing this. I want to share I shared with you the book, Annette Dobson's book, Generalized Linear Models, right?
Yeah.
So I want to share that one on the screen, the Generalized Linear Models. So for that document that I was looking at, the chapter, was it chapter 5 or chapter 15? You only need to understand the first 2 pages. That's what we need. The remaining, we get them from the Annette Dobson book. Is that okay?
Mm-hmm.
So allow me to Dobson book. Again, I'm sharing my screen. Are you able to see the book?
Yes. Yes.
So guys, this is the book that we are going to look at. The Annette Dobson book. I think it will do maybe a couple of lessons with it. So I'm going to chapter 3. Can you see chapter 3?
Yeah.
The exponential family. That's what we'll look at. Is that okay?
Mm-hmm.
And this will help us understand why we are using the different links. Is that okay?
Yes.
Nothing new there, just to understand why we are using the different links. Then once we are done with that one, then we'll do a couple of, we'll do the logistic regression in full, a few things about logistic regression and also Poisson regression. Then I think the syllabus also has something to do with survival. I'll check. I think it has survival analysis. Is that okay?
Yes.
The others, no, we don't need. Winbach's in Bayesian. So I want us first to focus on, so that we cement this thing of generalized linear model, so that we understand where these links come from. Is that okay? To understand that one, we must understand the exponential family. Is that okay?
Yes.
So I'm just scrolling to chapter 3. It's chapter 3. Go to the exponential family. We are there. Are you able to see it?
Yeah.
Okay. So I'm not interested in that one. I'm going to section 3.2. Can you see section 3.2?
Yes.
So we usually use the symbol. We usually use the symbol F, Y, theta to represent a general probability distribution. Is that okay?
Yes.
Let me differentiate between 2 things. When it is P, sometimes we can use P. Is that okay? For a probability distribution. Is that okay?
Yes.
But we usually reserve P for categorical ones, or rather discrete ones. But for now, just know that the F is also just a probability distribution, nothing else. It's a notation for probability distribution. Last week we were using P, but the F can also be used in place of as a notation for probability distribution. Is that okay?
Mm-hmm.
Then this theta, remember, theta is the parameter that governs that probability distribution. Is that okay?
Mm-hmm.
For example, for Bernoulli, the parameter is P. Is that okay?
Mm-hmm.
For Poisson, the parameter is lambda. Is that okay?
Yes.
So a general name for those P's and lambda, which are parameters for the distribution, we usually use theta as a general name for any of them. Is that okay?
Yeah. Yes.
So if we are dealing with the Bernoulli, then the theta becomes the P. Is that okay?
Yeah.
If we are dealing with Poisson, then the theta becomes the lambda. Is that okay?
Yes.
Now, for example, if I want to write the Poisson distribution, then I will write it like this: Fy theta is equal to E raised power negative lambda raised power y over y factorial. We wrote this last week.
Mm-hmm.
So ideally, I need to replace this theta with the lambda, because now I know for Poisson it is lambda. Is that okay?
Yeah.
So that now I write it this way. So that now I write it F lambda. Is that okay?
Yes.
Because now I'm talking about Poisson. Is that okay?
Yeah.
So now, if I just want to talk about a general distribution, then I'll be referring to that distribution as F of y theta. Is that okay?
Yes.
Now, section 3.2, we want to define what an exponential family distribution is. Is that okay?
Yes.
Any distribution, any probability distribution that you can write in this form. Can you see the form on the screen? Any probability distribution that you can write in the form where you have exponential outside, then you have AY. AY means a function of y only. Is that okay?
Mm-hmm.
Then multiplied B theta. B theta is a function of theta only. Is that okay?
Mm-hmm.
Then plus C theta. C theta is a different function of, it's a different function of theta only again. Is that okay?
Mm-hmm.
Plus dy, another function of y only. Is that okay?
Yeah.
So if we can rewrite any PDF and you can split it so that there's an exp outside, that is exponential outside, then inside the bracket we have three functions, a, b, plus c, plus d, where c is a function of y, of theta only, d is a function of y only, a is a function of y, and b is a function of theta. If we can write any distribution in this structure, then we say that that distribution belongs to the exponential family.
Mm-hmm.
Allow me to repeat. If we can take any PDF, rewrite it so that it has exp outside, and this function ay, a function of y only, b theta, a function of theta only, with a plus, another separate function of theta only, and another separate function of y only. If we can write any probability distribution in that form, then we say that it belongs to the exponential family. Is that okay?
Yes.
Allow me, let me give some space for people to ask questions on this exponential family. Yeah? Any question? Okay, let me proceed. Maybe a question will come later on. Is that okay?
Mm-hmm.
Now, on my screen, if we can write that function in this form of exponential family, then if AY, I hope you can see my screen. If AY is equal to Y, if we just get that the AY is just Y only, it's not Y squared plus 6, it's just Y only, then we say that the distribution is in canonical form. Is that okay?
Yes.
If the AY, if you write that that PDF in form of exponential family, and that AY is just Y, it's not Y squared or Y cubed or Y something, then we say that that PDF is in canonical form. Is that okay?
Yes.
And the B theta is actually called the natural parameter. Is that okay?
Yeah.
As you'll see later on that this function B theta is actually what gives you the link function. It's what gives you the link function. Is that okay?
Yes.
Now, let us take as one example for Poisson distribution. Assuming we have a Poisson distribution given by f of y, comma, lambda, which is given by e raised to negative lambda, lambda raised to y over y factorial. Is that okay?
Mm-hmm.
We need to write it in this form of 3.3. Is that okay?
Mm-hmm.
Without changing the equation. Is that okay?
Yes.
Now, so our f of y comma lambda will be equal to, remember we need an exp outside, exp, is that okay?
Yeah.
Remember exp is just, it's it's e, the natural, what is called the natural number e. Is that okay?
Yeah.
What cancels the e? Okay, let me put it this way. If I give you, let's say y is equal to 2 plus 3, is that okay? Sorry.
Yeah.
Y is equal to 2x plus z, is that okay?
Mm-hmm.
If I want to see a plus 10 here, is that okay? If I want to see a plus 10, is that okay?
Mm-hmm.
What can I do so that I introduce the plus 10 without changing this equation so that it still remains 2x plus z?
Minus 10.
A minus 10.
Exactly. So if I want to introduce plus 10, then the minus 10 can be introduced to cancel it. Is that okay?
Mm-hmm.
So addition cancels subtraction. Is that okay?
Mm-hmm.
What cancels square root? What cancels the square root?
Square.
The square. Is that okay?
Yeah.
What cancels multiplication? If I multiply by something, what can I do so that I nullify that one?
Division.
Division. Is that okay? Now,
Yeah.
if I introduce e, which is the natural log, and the natural number, what cancels the natural number? E. Something e raised for something. What cancels it?
Log.
It is the log. Log to base e. Is that okay?
Mm-hmm.
Is that okay?
Yes.
Okay, guys. Now, we want an exp, which is just the e. Is that okay? Exp is just e. Is that okay?
Mm-hmm.
It's not, we don't have it covering the entire function. Is that okay?
Yeah.
What can we do to our function? I'm rubbing this so that we are left with our function. We continue. What can we do to our function so that we have exp outside and the function still remains intact? I want to have EXP outside. What can I
Log.
do so that I need to introduce log? Is that okay?
Yeah.
Then I keep everything the way it is. E minus lambda raised to y over y factorial. So if I want to go back to what I have, then the EXP and the log will cancel out. Is that okay?
Yes.
Okay. Now we've introduced the EXP because we want it. We want to show. Remember, we are guided by this one here. Is that okay? We need an EXP outside. Somebody might ask me, why am I introducing EXP? Remember, we were trying to show that the Poisson belongs to the exponential family. So we need an EXP outside there. Is that okay?
Yeah.
Okay. Now let us proceed. Okay. Now we try and simplify the inside part. So we'll have EXP outside. Then here we will have log of e raised to negative lambda. What is log of A? What is this? Log A times B over C. What is that equal to? I think it's high school math. What is log of A times B over C?
Log A plus log B minus log C.
Correct. It will be log A plus log B minus log C, right? So that's what I'm going to use inside that bracket. Is that okay?
Yes.
So it will be log of e raised to negative lambda, right?
Yeah.
Then what will follow?
Plus log lambda raised to y.
Plus log of lambda raised to y. Then
Minus log.
Minus log of y factorial. Is that okay?
Yes.
But what will happen here? Here, what will happen here?
We will only have, I don't know, negative lambda.
Correct, because log and e cancel out, right?
Yeah.
So we'll have is equal to exp negative lambda plus still high school. What is log to base a? Sorry, log of a raised to b. If you remember, this was equal to b log a, right?
Yeah.
Yeah.
So we are using the same thing. So this will become y log lambda minus log y factorial. Is that okay?
Mm-hmm.
Is it in the form that we wanted? Do we have a place where we have ay times b theta? Remember, we don't have theta now, we are having y. We have a place where we have a function of y multiplied by a function of lambda.
Yes.
Where is it?
Y log lambda.
Y log lambda. So we bring it exp. So y log lambda. Is that okay?
Mm-hmm.
Plus, do we have a function of theta only, which does not contain y at all? It's theta only, standalone one.
Mm-hmm.
We have it?
Yes.
Yes.
Which one is it?
Minus lambda.
Minus lambda. Is that okay?
Mm-hmm.
Then do we have a function of y only, does not contain lambda?
Yes.
Which one?
Log y factorial.
Minus log y factorial. Is that okay?
Yes.
So we've actually written the Poisson distribution as an exponential family. Is that okay?
Yes.
In that case, what is ay equal to?
Y.
Y log.
Huh? Ay is y log.
It is y.
Y.
It's y. What about b theta?
Log lambda.
Log lambda, correct. C theta?
Minus lambda.
C theta minus lambda, correct. Then dy?
Minus log y factorial.
Minus log y factorial. Is that okay?
Mm-hmm.
And remember, I told you that the b theta is what will give you the link function. So for Poisson, what is b theta?
Log lambda.
For Poisson, it is log lambda. Can you see this is the link function that operates on, so the log into bracket lambda, which is basically telling us the link function is log for Poisson. Is that okay?
Yes.
Is that okay?
Yes.
Okay. Now, which is basically what we have here. Is that okay?
Yeah.
Okay, now for you to do, I'm giving you some 10 minutes to show that Bernoulli distribution belongs to the exponential family. So just to give you a heads up, the Bernoulli distribution is given by f of p is equal to f of y comma p is equal to p raised power y to bracket. So let us do binomial. Is that okay?
Mm-hmm.
Binomial. Then Bernoulli, I think, will be easy once you do binomial. So binomial distribution where? Given by ny p raised power y 1 minus p n minus y. Is that okay?
Yes.
Show that this belongs to exponential family. So remember the trick. The trick is first to introduce the exp because it does not exist. Is that okay? Then the next thing is to make sure you are rearranged so that you only have one place with ay. You cannot have ay in 2 places or 3 places. Is that okay? Again, you cannot have b theta in 2 places. You cannot have a function of theta, standalone function of theta in 2 places. It must be combined into one. Is that okay? So I'm giving you 10 minutes to do that. Is that okay?
Okay.
Is there somebody who can share the screen and write, or itakuwa ngumu? Okay, you guys do it individually, then you let me know. Guys, please don't go and use ChatGPT. It will do it for you, but it will be useless. You really need to try and understand how it works, because next time I'll give you a totally different distribution and you'll struggle. Is that okay? So it's 7:20, so 7:30 we regroup to check. So I would expect you to tell me what is your AY, what your AY is, what your B theta is, what your C theta is, and what your DY is. Is that okay? Is that okay?
Yes.
Yeah, so we regroup at, it's 7:20, we regroup at 7:30. So. Hello? Hello?
Yes.
Are you guys done?
Yes.
Okay. So what is AY? Okay, let me start with the link. That is what is interesting. B theta, what is B theta?
Is log of P over 1 minus P.
U over 1 minus P. Any other person who got it differently? Parfait.
Yes. Yes.
Ça va?
Ça va et vous?
Ça va bien. What did you get?
I was the one who gave the answer.
Oh, you're the one who gave the answer?
Yes.
Okay, the other guys? The other guys? Hello? Okay, Ian Joroge.
Yes,
What did you get?
I'm currently doing it.
Hii kitu ya dakika moja. You want to do it for 2 days. Stephen Oganga. Stephen? Stephen?
I also got the same answer.
Which one?
BQ is log P over 1 minus P.
Log P 1 minus P. Anyone who is struggling that needs some support? Anyone who is struggling?
Me.
Uh-huh. Now the problem is that you can't share your screen now. How do we help you? So, I mean, what can you tell us? Where are you stranded at?
I was not able to express the PDF in form of exponential family.
Yeah, we know we are doing that one, but at which step did you get stuck?
The very initial steps after introducing log.
Okay, so let me try. Let me try and do it here quickly. So we introduced log. We have exp log ny py 1 minus p n minus y, right?
Mm-hmm.
So we'll have exp. This will be log ny plus y log p plus n minus y log 1 minus p. Right?
Yes.
Did you get to that step?
Yeah, I got there. Now
Okay.
combining those two, the second and the third.
First, we can separate because this one we can see there's an ny, n and y, so we can separate because we need y separately. Is that okay?
Yeah.
So we can open it up. So we'll end up with exp log ny y plus y log p plus, if we open this bracket, then we'll end up with plus n log 1 minus p plus y log 1 minus p. Is that okay?
Mm-hmm.
We get another color. Okay, so we have y log 1 minus p, and we also have y log p. Is that okay? So we can factor out the y. Is that okay?
Yes.
So we'll have exp into bracket log ny plus y into bracket log p. So this is a minus, right? Log p minus log 1 minus p plus n log 1 minus p. Are you able to see that one?
Yes.
Then this one, these two, we can combine them. Log p minus log 1 minus p. What does it become if you combine them?
Log p over 1 minus p.
Correct. Is that okay? So we'll have exp into bracket y log p over 1 minus p, then plus some other things there. Is that okay?
Mm-hmm.
But already we can see that this one will be our ay, then this one will be our b theta. Is that okay?
Yeah.
So our link function is log of p over 1 minus p. Is that okay?
Yeah.
Calvin Otieno. Calvin.
Yes.
You told me that sometimes you try to play Avieta, I don't know, Betika. Ama, it was not you.
No, it was not me.
Anyway, but I'm sure you've heard of odds.
Yes.
You've heard of odds.
Mm-hmm.
What is odds? Is odds the same as probability?
I think it can be put the other way around as well. So it's not necessarily probability.
So odds is something else, probability is also something else, right?
Yes.
So what is odds? If I tell you what are the odds that it will rain tomorrow?
The chances.
But chance is probability. So are you telling me that odds is probability? Another name for probability is chance, right?
There is one by chance, and then that
chance is probability.
Which is okay. By chance, I think it doesn't necessarily come as a result of statistical computation.
I didn't understand.
Can come in there.
I mean, probability is something that comes with statistics. It's something that makes sense. It has some meaning. But chance is...
I'm just saying that chance is another name for probability. The chance of something happening is the same as the probability of something happening.
Okay,
Is that
now
okay?
the odds. What is just like
So
the
if the
opposite?
probability of raining tomorrow is 0.2, what are the odds of it raining tomorrow? So the odds of it rain, the odds is equal to probability of something divided by, sorry, probability of something happening divided by probability of it not happening. Is that okay? Steve?
Yes.
Steve?
Yes.
Steve?
Yes, I'm here.
To get the odds of something happening, you take the probability of that thing happening, divide by the probability of it not happening. Is that okay?
Yes.
If the odds, sorry, if the probability of it raining tomorrow is 0.2, so what are the odds of it raining tomorrow?
It will be 0.2. Let me take my calculator. 0.2.
No, you don't need to calculate. Just tell me the values.
Divide by 0.8.
Divide by
which will
1
give you
minus
0.25.
It is 0.2 divided by 1 minus 0.2. Is that okay?
Yes.
So if the probability,
0.25.
if the probability is denoted by P, what are the odds? The odds will be calculated using what? If the probability is P, so the odds will be equal to P over
1 minus P.
P over 1 minus P. Is that okay?
Yes.
Now, if I have it this way, how do you read this? What is this term? Read it for me.
It will be the log
What is
of
the name of log of?
Log of the odds.
Log of the odds. Is that okay?
Yes.
So log of the odds, a shorter name for it is logit. So logit stands for log of odds.
Okay.
Is that okay?
Yes.
So if I just write it as logit, I have to specify the probability P. So logit is another name for log of odds. So it is the same as log of P over 1 minus P. Patricia or Gijo?
Yes.
What does logit mean?
The log of the odds.
Log of odds. Is that okay?
Yes.
So guys, have you seen where the link for logistic is coming from? Remember, we've done binomial. So you can also do it for Bernoulli. You'll find that the link is still log of odds. Is that okay?
Yes.
So I leave it as an exercise for you to do it to show that Bernoulli distribution belongs to exponential family. Is that okay?
Yes.
Is that okay?
Yes.
Guys, I wish to stop there. So from today's class, what I expect you to know is where those link functions come from when you speak about GLM. Is that okay? Is that okay?
Yeah. Yes.
And for you to know where they come from, you must understand exponential family and its structure. Is that okay?
Yes.
Is that okay?
Yes.
By now, you should be able to write a PDF, or assuming that it belongs to exponential family, you should be able to check whether PDF belongs to exponential family. Is that okay?
Yes.
So notice that I can give you the PDF. For those that I know that you do not know, I can give you the structure of the PDF. Then you just continue working. Is that okay? For some like Poisson, binomial, Bernoulli, exponential, those ones I will not give you the PDF. I expect you to know them often for those few PDFs. Is that okay? Or other probabilities? Is that okay? Is that okay?
Yes.
Okay. So it's showing here for binomial, it's showing there. Allow me to capture these properties in the next 10 minutes, then we break. Is that okay? Properties of distribution in the exponential family. Once you know that a distribution belongs to the exponential family, then there are some properties about it. Is that okay?
Yes.
The first property is that let me just get the screenshot. There are two main properties. Let me just put them that way. The first one is this one. Is that okay?
Mm-hmm.
That to get the mean, to get the expected value of the AY in that exponential family, you only need to differentiate the C function divided by the B function. Is that okay?
Yes.
So to get the expected value of AY in that exponential family, you only need to get the derivative of the C function and also divided by the derivative of the theta function. Is that okay?
Mm-hmm.
Let me ask you, what was C theta for Poisson and what was B theta in the Poisson? Do you remember that?
Negative lambda C theta for Poisson.
C theta was negative lambda and the B theta?
Log lambda.
Log lambda. Is that okay?
Mm-hmm.
Is that okay?
Yeah.
Now, what is C theta prime? C theta prime is just differentiating C theta. Is that okay? This is the same as D over D theta of that C theta. If you differentiate that C with respect to theta, by now we are differentiating with respect to lambda. What is of D C theta over D lambda? If you differentiate it with respect to the parameter lambda, what do you get? This is C theta. If you differentiate it with respect to lambda, what do you get?
I think 0.
Nope.
Get -1.
You get -1. Is that okay? It's like f of x is equal to negative x. Differentiate this with respect to x. It will be -1. Is that okay?
Yeah.
Then b theta, d of d lambda of b theta. What do we get? Differentiate log lambda with respect to lambda. What do you get? For example, if I tell you that f of x is equal to log x, what is f prime of x? That is the derivative. Hmm? Hmm?
Is it 1 over x?
It is 1 over x. So what is the derivative of log lambda?
1 over lambda.
Lambda.
It is 1 over lambda. Was it log lambda or was it minus log lambda? The b theta.
I think it was minus.
Just confirm. Ah, no. It's not. It's us. No, this one has a negative. Can you see here? Can you see it? It's a negative here. Unaiona? Can you see it? It is negative c prime of theta divided by b prime of theta.
Yeah.
Is that okay? Equation 3.9. There's a negative. Is that okay? So now, if we take c, what was our c prime of theta?
Negative 1.
So it is negative multiplied by negative 1. Then what is b prime of theta? What is b prime of theta?
1 over lambda.
1 over lambda. So when you evaluate this, what do you get?
Lambda.
Lambda. But what is ay in Poisson?
Negative lambda, I think.
Ay, no, ay.
Oh, ay is y.
Ay is y. So in short, it is telling us that the expected value of y is equal to what?
Lambda.
Lambda.
Is equal to lambda. So here we are also proving and showing you that the expected value for Poisson response variable is actually lambda. Is that okay? Is that okay?
Yes.
So guys, look at this. Wait. Okay. For variance, to get the variance of ay, to get the variance of ay, again, this is the formula. Is that okay? Let us try and do it let us try and prove this one. Is that okay?
Yeah.
Just for 3 minutes, I just take you through. I hope you're able to see my screen. Is that okay?
Yeah.
So remember that if assuming that f of y theta belongs to the exponential family, is that okay? So if you integrate any probability distribution with respect to with respect to the random variable y, what do you usually get? Remember, integration is the same as summation if it is discrete. If you sum all the probabilities, what do you usually get?
1.
Usually get 1. Is that okay?
Yeah.
So the same thing, if you integrate the entire PDF for all values of y, you get 1. Is that okay?
Yeah.
Now, differentiate both sides with respect to theta. Also both sides with respect to theta. If you differentiate 1 with respect to theta, what do you get?
0.
Because it's a constant, you'll get 0. Is that okay? So on the left-hand side, we'll be left with this. Can you see? We'll be left with this. Is that okay? Then we can take the derivative inside. We can move this derivative to go inside the integration. Because remember, you can integrate, then differentiate, or differentiate, then integrate. You'll get the same answer. Is that okay? Now, inside, we are differentiating the f of y with respect to theta, then dy is equal to 0. This 0 is coming from this part here. Is that okay? Again, if you differentiate again, second derivative again, with respect to theta, both sides again. If you remember on the right-hand side, we have 0. Is that okay? If you differentiate again with 0 with respect to theta, you'll get a 0. Is that okay?
Yeah.
But if you differentiate inside, we had already done first derivative. So if you differentiate, then you get the second derivative. Is that okay?
Yeah.
Now, remember, the f, we say that the f is exponential family. So we can write it out as exponential family, which is this one. Is that okay? Now we need to differentiate it once. Remember, we are differentiating it twice, right?
Yeah.
So we are doing the first derivative of that f of y. So we write that f of y in exponential family, but now we are differentiating it, the first derivative with respect to theta, then again we'll differentiate it. Is that okay? To get the second derivative. Is that okay?
Yes.
Now, let us differentiate this inside thing with respect to theta. What do we get? First of all, remind yourself, if y is equal to e raised by x squared, what is dy dx? If y is equal to e raised by x squared, what is dy dx? Okay, let me make it simple a little bit. If y is equal to e raised by 2x, what is dy dx?
I think it is 2x exponential 2x.
So the way to differentiate this is look at this as a single thing. Is that okay? Is that okay?
Yes. Yes. Hello?
Yes, yes, yes.
Okay.
Just 1 second. Hello?
Yes.
So to differentiate this, how do you differentiate it? First, anytime you see an e raised by something, to differentiate it, first you just write it the way it is first. The derivative, you write exactly the way it is first. Is that okay? Without touching it. So you keep it as e raised by 2x first. Is that okay?
Yeah.
Then you multiply this with what you get when you differentiate the power. So when you differentiate this power, what do you get?
2.
2. So the trick is first, if you are told to differentiate e raised by something, first you just write it the way it is, e raised by that thing first, then multiply by the derivative of the power. Is that okay?
Yes.
So now that's what we are trying to do here. We are differentiating. Sorry. We are differentiating this. So what do we do first? What did I say we do first?
Write it first the way it is.
We write it the way it is. Is that okay?
Yes.
So I will write this the way it is. Is that okay? But recall it is this one. Is that okay?
Yeah.
So I can just take it first and put it inside there. Can you see it there?
Yeah.
So it's like I've rewritten the right-hand side. Is that okay? Then now here, I differentiate whatever is inside, inside the power. I differentiate what is inside the power with respect to y. Is that with to theta? Is that okay?
Yeah.
So let us start with, so we are differentiating what is inside the power now. Is that okay?
Yes.
So anyone who doesn't see where this one is coming from, this part first, that bit. Anyone who doesn't see where it's coming from. Is that one clear?
Yes.
The yes is not strong enough.
A bit more.
Is it okay?
Yes.
Okay. Now,
I think there's someone speaking. I don't know.
please
who
speak
it is.
loud.
Sorry, I'm requesting if you could expand your screen a bit more.
Okay, sure. Is it better?
Yeah.
Yes.
Okay, sorry for that. So let me repeat again. Remember we said that when differentiating anything, e raised to power something. Is that okay? We first just write the e raised to power something, the entire of it, we put it down, we write it down. Then we multiply, so we first write the e raised to power something, then we multiply that e raised to power something by the derivative of this something. We differentiate the power. Is that okay?
Yeah.
So in our case, we have to write the entire of the right-hand side. Is that okay? Down first. But what is the right-hand side? We know its name from the left-hand side. What is its name on the left-hand side?
Fy theta.
Fy theta. That's why we are putting this Fy theta here. Is that okay? Then now we go and differentiate inside this blue rectangle. Sorry, the power. Sorry, not the blue rectangle, but the power. We now come and differentiate the power here. This one. Is that okay?
Yeah.
Now, I'm starting with the easier one. If we differentiate this with respect to theta, what do we get? If we differentiate dy with respect to theta, what do we get?
0.
We get 0 because it's a function of y. It does not contain any theta. Is that okay? Is that okay?
Yeah.
So it disappears. Then if we differentiate c theta, what do we get? We can just write it as c prime theta. Is that okay? We don't need to derive its differentiation. Is that okay?
Yes.
Why am I not writing d prime y?
Because it is 0.
Guys, why am I not writing d prime y?
Anything multiplied by 0, it will be 0.
No. Why am I not writing d prime y? Why am I writing c prime theta and not d prime y?
Differentiating with respect to theta.
Differentiating differentiating d into bracket y with respect to theta. dy means it's a function of y only, does not contain theta. So with respect to theta, dy does not contain theta, so it's a constant. So anytime you're differentiating a constant, we'll get a 0, right? But c theta is a function of theta, so we need to differentiate it. So just to show that we'll differentiate it later on, we just give it a prime. Is that okay?
Yes.
Now we are left with this one here. Is that okay? Sorry, I'm using the same color. We are left with this one here. Ay multiplied by theta, b theta. Remember, ay is a function of y, which does not contain theta. So it means we'll just be differentiating the b theta bit. So we'd end up with ay b theta. Is that okay? Is that okay?
Yeah. Hello, you can't hear me?
Yes.
We
Yes.
can't hear you.
No, I'm not speaking.
Okay.
So are we okay up to this point?
Yes.
So we need to multiply this. Sorry. We need to multiply this with this, and we just distribute them. Is that okay?
Yeah.
So we'll end up with the integral ay, let me write in blue. It will be the integral of ay b prime theta f of y theta d y. That's the first part. Is that okay?
Yeah.
Then plus, that is this part. We've just opened up this one and brought it in. Is that okay?
Mm-hmm.
Then the second part will be, we distribute the integral plus the integral c prime theta f of y theta dy is equal to 0. Is that okay?
Yes.
We just distributed this to this and again to this because there's a plus. There's this bigger bracket that is multiplying them. Is that okay?
Yes. Yes.
Is that okay?
Yes.
I repeat again. So we are just taking this one. There's a big bracket, this one here. So we are distributing and this. We are distributing the integral, but after multiplying this outside, we are opening the bracket. Is that okay? Is that okay?
Yes.
So we'll be left with the integral. So the first integral, the first one is ay b prime theta f of y theta dy, and the second one is the integral c prime theta f of y theta dy. Is that okay?
Yes.
But we are integrating with respect to y, so it means c prime theta is a constant. Is that okay?
Yes.
We can remove it outside. Is that okay?
Yes.
What will be left inside?
Fy theta.
But there's an integral. Is that okay? This one.
Yeah.
So we are integrating over the fy theta. If we integrate over fy theta, what do you get? If we're integrating the PDF only, if you integrate the PDF only, what do you get?
1.
You get 1. So we'll be left with 1 times the c theta that we removed outside. This theta that comes out, then whatever is remaining here will be equal to 1. So it will be 1 times c theta, which gives us this one. Is that okay?
Yes.
Then on the second part, again, we remove b theta outside, and it's this b theta that we have here. Is that okay? We are left with, let me wrap this. We are left with the integral of ay f y comma theta dy. The first part, we are left with that one, with a b prime theta inside, b prime theta outside. Is that okay?
Mm-hmm.
Have you done random variables? Anyway, how do you get expected value of x if you're given a PDF? If you're given a PDF, the expected value of x is given by the integral of x f of x dy. Is that okay? So
Yes.
what is this part here? Are you able to give a name to this part using that information? If this
Is it
lower one is
expected?
if this lower one is expected value of X, what is that upper one, this bit here?
Expected of Y.
It is expected value of AY.
Oh, Y.
It is expected value of AY. Is that okay?
Mm-hmm.
So it means it will be expected value of AY. This one, it will be expected value of AY times B prime theta, which we had to remove outside. This one is the C prime theta is equal to this. Then making expected value of Y the subject with the formula, you get this. Is that okay?
Mm-hmm.
So this section, we are just proving that if you have a PDF and you can write it in exponential family, then if somebody asks you what is the expected value of AY from that exponential family, you don't need to calculate it. You only need to go and get the C theta and B theta and arrange them in this form, and you'll get the expected value of AY. Am I making sense?
Yes.
And we can actually use this to show that the expected value of X, where X is a Poisson, we'll find it that it's lambda. We've already shown that one previously, that example when we are starting. We can also use it to show that expected value of X when X is Poisson. So this one is for Poisson. When X is Bernoulli, then this one will be P. We can use this to show that for those who are doubting before. Is that okay?
Yes.
Guys, bottom line, if you can write your distribution as exponential family, then you can actually also show that the expected value of that response variable, you can get it by just differentiating these two functions and dividing them in, dividing one divided by the other. Is that okay?
Yes.
Guys, please. The same thing, we can also derive the variance, which is what is being derived at the bottom here. Is that okay?
Yes.
Please go through those two properties of exponential family. If you have any challenge during the week, drop me a message any place that you don't understand. Is that okay?
Yes.
Feel free to screenshot and circle and tell me, you know, I don't understand how this part opens up. So I wish to stop there for today. Is that okay?
Yes.
Great lecture today. Thank you.
Okay. So enjoy the rest of your evening.
You too, thanks.
Bye.
Bye.